Awesome. Welcome back. So now we need to start plugging this stuff in. We have, we already know our NF and NI. H should be a constant. Granted, I'm still gonna have to probably look it up, but it should be a constant. And then do we have A? Wrong way again. Let's see. What in here could be A? It's either gonna be this 22 or I know A is going to be the length. Oh, sorry, what was that?
Sorry, I was talking to my daughter. She's talking.
Okay, no worries. No worries. I'm just looking through my notes trying to find the A. These length of the box. M is massive particle. And since we're dealing with like conjugations and electrons, that's gonna be the electron. H is our constant. Which I believe should be, according to my note, 23. No. 6.626 times 10 to the negative 34 joules per second. No, joules seconds. And the mass of an electron, 9.7 times 10 to the negative 31 kilograms. I still don't know what A would be. Is it going to be this? I feel like average internuclear distance. All right, we're going to have to be dealing with this up here. So let me clear some space. So we have our average internuclear distance being 120 ppm, and then 20 conjugated C bonds. So we have conjugation, which kind of looks like this. And there should be 22 of those, and there should be 40 between the nuclei. So I think we're just gonna do 140 times 22. Let's see what that gets us. That gets us 3080 PM. And P is pico, which is smaller than nano. Yeah, it's not going to be on there. This is something that I probably memorized Or she gives, oh, maybe she gives it in a constant. She does not. Okay, fun. I'm gonna check the key. Let's see. Okay, cool. We've been doing good so far. Isolated the E. Um, that looks like what I wrote. That, yeah, good constant. Then this is gonna be our A. I'm gonna write it down and we're gonna try and figure out why that's our A. 4 times 10 to the negative 9 meters. This doesn't feel too far from there. Let's also look up what the pico is. Pico is 10 to the negative 12. How did you get negative 9 from there? Oh, maybe because there's there's that many carbons in a conjugation, so you're gonna be needing to multiply by 2, in which case it would be and then there's 20 of those. So if we do that multiplied by 2 times 2, 2, that gets us 61, 6. That's not what she has. I guess I can see that. Okay, so I'm not entirely sure why she has the length of the box and the key as that value. I'm not sure where she's getting it. But we'll continue with the value that she has. And because I'd rather not give you guys the wrong value. So anyway, from here we go ahead and plug stuff in with F being, oh yeah, we also have that over here. Being 12 squared minus 11 squared. And then our constant, 6. I could probably copy and paste it. squared over I'll do this one in black since it's not really my number. 9 meters. And then the electron. Oh, that needs to be squared. And then we can go ahead and plug that into our calculators. So for this part, I got 23. This is where she got the 23 from in her key. E to the negative 4 squared. Eight times
'Cause I don't know if I plugged this in right, but I got 1.6 times 10 to the negative 19.
Yeah, I got the same.
All right, cool.
And then the units for that. We're gonna have joules seconds both squared over meters squared and kilograms. Joules, I believe, are Newton's meters. So that becomes Newton squared, meter squared, second squared over meters squared kilograms. Those two cancel out. I believe Newtons are MA, kilograms, meters over second squared, which that's gonna get us get rid of one of the second squared, kilograms, get rid of one of the kilograms. Which gets us kilograms meters squared over seconds squared, which is joules. No, which is newtons, which is what we expect for energy. So that's good. And then I'm gonna go ahead and double check with the key. That is next one. What was this? She got joules. And she does not put where she, oh, she got the A here. One, 4 times 10 to the negative 10 meters. I think we were very close to how we were trying to solve this. Because we use a 22. We use a 22 here, but that's 22 bonds. It's not, it's 22 carbons, not 22 bonds, right? Because like here we have 4 carbons, but 3 bonds. So it's going to be removing 1. So that's where she got the 22, sorry, 21 from. So that's what she did. This became 21. In which case this would have been 140 times 21. Oh yeah, that would have been 2940 picometers. And then we have picometers is times 10, 12, and then we go 1, 2, 3, 12 minus 3. How'd you get 10 from that? Oh, she got 10 because it was 1. Minus 2. Okay, so we were close. We just had a wrong number. Go ahead and erase this then. Maybe back to the units. Oh, I see. I have a second squared up there. It is joules. So then that's going to be Newton's meters, which is joules. Okay, cool. We're good. Cool. So that's that problem. And I'm glad we figured out where that A came from. And it looks like that's the end of time that we have. If you guys want to stay, I still have time. If you guys want to go through number 4 and then go back and do number 2. Otherwise, you're free to go. I'll probably just keep recording.
Number 2 is a free response, right? The one with like the explanation or like
Yeah, it says use your own words. So I haven't done some research, so I gotta go look online for that.
okay, it's okay. These are the ones that she has posted, right?
I don't
These
know.
questions.
She sent them to me to work with you guys on, so
Okay.
I don't have
Thanks.
access to your Canva, so I don't know.
That's okay. I think because some of it looks familiar, but it may be because I was looking at the practice packets.
Okay, cool.
Yeah.
Yeah, cool. Okay. Go on to number 4. Let me see if I can clear myself some space over here. Let's erase that. Then yeah, it looks like we should have enough space for one more problem. Okay. Given the wave function below, calculate its eigenvalue using the Hamiltonian operator, expectation value, and then should the expectation value be different than the eigenvalue? So let's start with the equations for those, because I'm gonna need to grab them for my notes. The Hamiltonian operator. Summation. Here it is. Hamiltonian. Negative Good. M like, and then we have our expectation value. Be somewhere. Here it is. And then our expectation value.
The expectation value is the one we don't have to solve like fully through, right? It's the one we just set up.
Yeah, you just set up. If she asks you
Okay.
to solve you, she's being mean. Infinity star. I'm gonna write this A different color because I have it in a different color in my notes. Which means it's either important or hard to see. A. Oh, that's why I have it bolded. Over the same thing without the A. Cool. And then just a reminder that expectation value is our average value. And if system, there's not an I. If system in A, there's two options, single. Dates. Then we have, I guess I'll put then. Then expectation value is equal to eigenvalue. I'm blanking on what eigenvalue is supposed to be written like. I think it's just an E. It's the O. Yeah. And that's because if it has like a single eigenstate, then it only has one eigenvalue and your average should be that one value. But if it has multiple eigenstates, then your expectation value is the average of all those, and it's not really going to equal any one of them. Also know that when it's a single, it's considered pure, which means you have an eigenfunction. Usually. I don't think she's ever said that, but that's what I've noticed. Like if you have an eigenfunction, then your expectation value is usually going to equal your eigenvalue. Anyway, I'll go ahead and continue this. Calculate eigenvalue using the Hamiltonian operator. So we have h wave function is equal to eigenvalue wave function. We're going to focus on this side here. And we're going to put negative squared over 2m squared over 2 squared. I guess I should probably put that one further back. I'll leave it. Amen. And then we're going to go ahead and derive it. I'll move it back. Just because this is our notation for the derivative. So we're going to hold off on this side for now. We're just going to focus on this bit. It's an e, so it's probably going to become like squared. E to this stays the same. Not sure if it's going to be negative. I feel like it probably would be because you grab it. Bring it down. And then we're just going to have our partial derivative once more. Do I have a 2 under there? Is that right? We'll check that. Oh no, my notes are just wonky. It's in tx squared. Erase those. Except it's not squared anymore because we already did one derivative. And then we're going to go ahead and derive it again. Which I think this time it should go back to positive. This time it's going to be 3 because we're going to drop down. It's an e, so that's going to stay the same. I'm just going to double check that before we move on. Yeah, that looks right. Cool. And then from there, we can bring this back down. So that we get negative squared over 2m wavelength 3, then e negative wavelength x as our formula, and that's going to be equal to our eigenvalue wave function. Our eigenvalue, then you're just going to need to extract the wave function from here. So we only need to remove 2 of these because our original wave function already had one. 2m squared, and then our wave function a minus. So then this part is our eigenvalue. And then this part is our wave function, which means that this was an eigenfunction. Right? Because if you have an eigenfunction, then you should be getting your eigenvalue out from that. And I believe that answers that. Calculate the eigenvalue. Yep, we calculated the eigenvalue. So and of course you could probably simplify that and plug things in, but I think for now that should be quite enough. And then we set up the expectation value. I'm gonna go ahead and grab this and move it because that's gonna be a lot to deal with in terms of space. And we're setting up the expectation value. I want to copy and paste that. I think I will. Oh shoot, our meeting's gonna end in 10 minutes again, huh? Okay. Anyway, we have our wave function. I'm gonna write it at the bottom first just because it seems easier. That's probably just gonna be squared. Yes. Just because it's multiplied by itself. So yeah. Then up here, I'm not sure if you're supposed to write it separately. My wave functions are struggling today. They're not wave functions, they're wavelengths. I guess we will just write it fully, just think to be safe. Yeah, I'd probably just write it like that just to be safe. And I think that should be it. Oh wait, no. This A here. We have to plug in the A. I think this A is it an operator? I feel like it might be an operator. Okay. So I am gonna write the wave function twice just to be safe on both sides. As for that A, let's give us some room. I think because we use our Hamiltonian operator, that's what our A is gonna be. So it's saying that it's whatever operator you used, I believe. So in which case, write it in pink. Negative h squared 2m d squared over, sorry, it's delta squared. And that should be our answer. I'll move this closer just because it's nicer. And then we'll go ahead and double check this. Yeah, cool. That was right. And the value should be the same. Yeah, it should be the same because we saw that we got the same wave function back. And because we got the same wave function back after putting it into our operator, it means that that wave function was an eigenfunction and it should be pure. In which case it would fall under here, the single eigenstates, because it's pure and has an eigenfunction. So our expectation value is equal to our eigenvalue. And then with that, I think we should be good. Are there any questions?
No, I don't have any questions for right now.
Okay. right. Well, thank you guys for staying 15 minutes extra. I hope this was helpful, and I hope you guys have a nice weekend.
Thank you,
Thank
Dee,
you.
for going over it with us. We appreciate you very, very much. Have a good weekend.
You too. Take care.
Bye.
Bye. Alrighty.